So here's an example of an LRVP that we commonly see in our power plant applications. Here we have a two-stage pump. The suction line here, which comes into the first stage. You have the second stage over here, and then this is the seal water and air tank. And the seal water is pumped out of this tank through this heat exchanger here, and then back into the seals up through this. The cooling side of this shell tube heat exchanger is typically the same source as the main condenser in a power plant, which is either from a cooling tower, river, lake, or ocean typically. The first case study I'm going to go through is a plant with two of these pumps, and our customer, I believe that one of his pump was degraded, but didn't have the data to prove to his maintenance manager that the pump was in need of service. So we installed one of our probes, and in the first week of service, he did a pump swap to compare his two pumps. The data from the pump swap is here. Now for an LRVP, we want to focus on volumetric flow rate, or ACFM, which is this black line here on this axis. The left side of this plot is the pump that he was questioned. They're labeled pump 62. So he was running, collected the data with pump 62, performed his pump swap here. So now he's running pump 61 only over here. And you can see the ACFM actual cubic feet per minute went from about 500 up to almost 2,000. So it almost quadrupled. So with this data, our contact now had the evidence he needed to go to his management team and get the pump service approved. It also provided them to know which pump they should be running to maintain the lowest possible pressures in their condenser vessel. What's interesting about this case study is it gives us a little bit more information as we start to trend and look at this pump 61 data over the next 6 months. What we have here is the trend that I use to benchmark and monitor pump capacity over time. So you'll plot ACFM, or the volumetric flow rate, versus suction pressure, two parameters on the instrumentation. So what I have here is data fall over the next 6 months, and you can see it's color coded. So the dark blue is in December and transitions to red in June of that year. So first off, we have this little data set here. That is the data from pump 62 that we saw in the previous class. So the degraded performing pump here. The rest of this data is pump 61, so over the next 6 months. And as you can see, as time goes on, you get this capacity relationship, this is a pretty typical liquid ring capacity relationship of pressure versus volumetric flow rate. But you see what looks like the pump capacity dropping off over time. And what is actually happening here is this is dropping off, but it's not a function of mechanical degradation. This plant is located on the Mississippi River up in Minnesota and uses the river as its cooling water. Well, in the winter months, the river water temperature is in the mid-30s, and it can get as high as the 80s in the summer months. So this river water is what was used to go through that shell tube heat exchanger I showed on one of the previous slides. And this drop off in pump capacity with time is actually a direct result of your seal water temperature increasing over time. So this pump 61, which is a good working pump, you have this very defined, definitive relationship between seal water temperature and pump capacity. It is important to note that this is only one of many forms of degradation that can take place in pump performance monitoring.